Just let me know if you see the whole full screen when I put it.
Just try to change one slide.
Okay.
I think yes, there is. Yes, okay, no problem.
Okay, perfect.
Okay, so we can start. So welcome everybody to the analysis junior seminar of today. So today we have the first speaker that is not from CISA. We have Lorenzo Portinale, that is a PhD student in IST of Vienna under the supervision of Professor Jan Mas. And we'll talk about discrete-to-continuum limits of transport problems and gradient flow evolutions.
Thank you very much, Manuela. Thanks a lot for the invitation. Of course, I would have enjoyed a lot to come to Trieste, but I guess we can postpone this to future times. Okay, yes, as you said, I will essentially present an overview of what has been my PhD thesis in progress. As you said, my supervisor is Jan Mas. I work at IST Austria in Vienna, or close to Vienna. And this also includes some collaboration with a former PhD of Jan, Dominique Forket, and also Eva Kopfe and Peter Gladbach. So what I want to do is to sort of give an overview about transport problem, both at the continuous and at the discrete level, and also discuss the connection to gradient flows. So what I decided to do is, of course, I don't know exactly the background on everybody, so I will try to be not too technical, and please feel free to interrupt me and say that the things are not completely clear. And so let me start, for example, from the basic definition from which I want to start my discussion. Okay, so the first one is essentially the classical definition of transport problem. So the first topic I want to discuss is optimal transport in Euclidean space. Okay, so the main character is the so-called Bus-Time-to distance, or the Kantorovich formulation in RD. Okay, so this is a variational formulation, variational problem. So given two probability measures, described in this picture by these two distribution of masses, we are interested in studying this variational problem that is describing all the possible ways to transport the mass from mu to nu, and this mathematically will be described by a probability pi, which is called transport plan on the product space, which has the right marginal mu and nu. This is a mathematical formulation to say that the pi is describing a transportation from the measure mu to the measure nu. And between all the possible ways to transport the mass, we are interested in minimizing proportional to the distance to the power 2 of the transportation. So if the point x goes to the point y, I pay a price, which is the square of the distance. I said it is a distance in the sense that it is in fact a distance, so we can endow the space of probability measure. In fact, to be precise, the space of probability measure P2 in the sense of we also assume to have second moment finite. This is sort of intuitive. If you imagine this, we have a quadratic cost. So if we want to be a proper distance and not an extended distance, we need to assume the measure to have second moment finite. And this defines a distance on the space of probability measure. So this is what I would call the static formulation of optimal transport. And there are many, many different equivalent formulations. And I want to focus on one specifically, which is a more dynamical perspective on this problem. Okay, so the dynamical perspective of formulation of the Bus-Time-to distance has been introduced by the seminal work of Benamou and Bernier, where the authors show that there is an equivalent way to consider this distance. And this equivalent way is not of static nature, but rather more dynamical perspective. Okay, and the formula reads as follows. You can consider a second variational problem, which instead of looking at the possible static transportation, you look at all the possible evolution, mu t, of measures. So it's a curve in the space of measures, from the measure mu0 to the measure mu1. And the transportation is described by this continuity equation. So you can think this as psi t being a flux, and describing exactly the motion of the particles from the first support of the measure to the second one. And between all the possible ways to transport the mass from mu0 mu1, we want to minimize the total kinetic energy. It is a fairly reasonable transportation problem, but it's not so immediate to understand that these two formulations are in fact the same. They are very different in nature. One is static, the other one is dynamical, and the beautiful result is exactly the fact that two formulations are indeed equivalent. Okay, so in this picture, you really see just a possible admissible transportation between time 0 and time 1. Okay, so this formulation, this dynamical point of view, is crucial for what I wanted to discuss next. It has been like the starting point, both to discuss connection to PDEs and gradient flows, but also to discuss, to talk about discrete optimal transportation problem. So what I want to start here first is the connection to gradient flows. Once again, I believe it is a good approach to this framework to really start from the basic final dimensional and smooth setting and try to understand the key notions which are connecting these PDEs, the evolution equation to the optimal transportation. So let's start very simple. So let's consider RD and an energy functional E from RD to R. Okay, here in the picture it's even easier, just a one-dimensional picture. Okay, and when I say gradient flow with respect to this energy, I mean exactly this evolution equation. Okay, so the time derivative of the curve follows minus the gradient of the energy in the point for some initial datum x0. So the idea is that we want to follow trajectory following the direction of maximum decreasing properties of the function E. So in some sense, minus the gradient is really the steepest descent, the sort of the best direction in order to decrease the function E. And this evolution really follows the maximum decreasing direction of the functional E. What I want to do here is a easy computation in finite dimension, but it's a key computation to move to the infinite dimensional setting. So suppose we have any curve, xt, and with any curve I mean not the solution, just simply any possible evolution. And let's try to compute the energy dissipation. So the energy dissipation, I mean how the energy changes along time, along the evolution xt. So if I compute this, I can simply use the chain rule and just get x dot times the gradient. Okay, and sort of simple Cauchy-Schwarz inequality says that this cannot be smaller than minus the product of the speed times the modulus of the gradient. Okay, and another sort of simple Young inequality also shows that this cannot be more negative than this quantity here. So it's a kinetic contribution here plus minus the square of the gradient. So this inequality holds true for all the possible curves. So there's no way you can get a dissipation which is smaller than this negative number here. But if you pay a bit of attention here about this inequality, if I reverse the inequality, so if I look at when actually these inequality are equalities, you can easily convince yourself that to get equality in Cauchy-Schwarz and also to get equality in the Young inequality, you need exactly to satisfy this equation. So in other words, if I reverse the inequality, the equalities are true if and only if you actually satisfy the evolution equation. So in some sense, it's a different formulation of the same equation. Okay, so this inequality here is equivalent to the first line in this definition above. Okay, if now I also want to take into account the initial datum, I can simply integrate in time. So if I integrate in time, I get exactly this. I get what is known as energy dissipation inequality, so EDI formulation of this system. It's called dissipation inequality also because, as you can see here, the energy is decreasing as we expected, and you can also quantify precisely how fast the energy is decreasing. It is decreasing proportional to the square of the velocity and the square of the gradient. So this is a completely equivalent way to formulate the gradient flow equation, but on the other hand, it's very different in nature. In some sense, this equation is a pointwise condition. This is much more a sort of energy balance condition and doesn't involve exactly pointwise condition, but more the total contribution at the level of the dissipation. And this is crucial if I want to move to infinite dimension, because in infinite dimension, condition like this might be more complicated and can also, in general, they don't really make sense if you don't really go through much more complicated situations. So one natural thing is to take this possible equivalent formulation to define gradient flows in more complicated settings. And because I want to talk about optimal transport, I want to talk about connections with that, the infinite dimensional setting I have in mind is exactly the space of probability measures. So suppose now that instead of working on RD, I take an energy which is a function from the space of probability measure over R plus, for example, supposed also to be usually convex. What I want to say is that I want to define a solution to this inequality, giving meaning to these two objects. a priori, especially the gradient, is not something which is well defined in a generic metric space. So we need to give a meaning to this object. And this is generally possible. It's possible in the following way. So first, the time derivative, so the speed, can be defined using the so-called metric derivative. In some sense, it's the intuitive way to do it. If you are in RD, what you take is just simply take the difference of the curve and you divide by h. Here, instead of taking the difference, you take the distance. Okay, so you take the distance at time t plus h from t plus h to time t. You divide by h and you take the limit to 0. Some non-trivial result says that if the curve is sufficiently continuous, such limit exists, at least almost everywhere. And you define this as the metric derivative. The same thing can happen also for the gradient. We don't really give a notion to the gradient in the point-wise sense, but the modulus of the gradient can be defined. I will change notation just to remember it is not exactly a gradient, and this is called the slope of a functional e. And the slope is done in the similar way as you do in Euclidean space. You take the difference of the energy between nu and mu, you divide by the distance as you usually do in RT, and you take the lim sup as nu goes to mu. Here you take the lim sup because the existence of the limit is more tricky than the one of the metric derivative here. So with these two definitions at hand, I simply say that a solution to a gradient flows of an energy on the space of probability measure is simply given by a solution to this inequality. So the point here, the takeaway message here is that I don't really have a notion of gradient like in the previous sense, but I can still give a meaning to this inequality. And I will simply define a gradient flow solution to be a solution to this inequality. Okay, so I want to give you an example here. In fact, this is not a pure abstract playing around, but it can be really useful in connection to PDEs. So some PDEs can be represented and sort of equivalently recast as solution to this inequality. The classical example is the heat flow, or even more in general, the Fokker-Planck equation. The Fokker-Planck equation is simply an evolution PDE where there is a diffusion part here, Laplacian, and a transport term driven by a sort of C1 potential on RD. I mean, it's not immediate, but one can convince himself that this PDE, one can prove it, is totally equivalent to, in solution to an ADI, an inequality as before, when the energy with respect to whom we take the gradient flow is the so-called relative entropy. So it's a log-free entropy that gives rise to the diffusion term plus an external potential, which is the one that corresponds to the transport equation, to the transport term of the equation. So this is very important. In some sense, you say that there is a class of PDEs which can also be reinterpreted as gradient flows in the space of probability measures. And this gives you a new perspective to study those equations, new point of views, and also new properties of this equation. For example, you can quantify specifically the dissipation of the entropy along the solution, exactly studying the behavior of those objects involved. Okay, so this is the first connection, optimal transport to gradient flows. But as I promised in the title, my topic of discussion is the connection between discrete and continuous spaces. So what I want to talk about now is the discrete counterparts of this problem. Okay, so the next slides will be devoted to the description of discrete optimal transport. Okay, so this was the formulation that I told you before, this linear formulation of optimal transport. And what I want to say now is that there is a reasonable way to talk about a discrete version of these formulas when we work on discrete settings. So what do I mean with discrete setting? I mean the following picture, okay, at least for this talk. So X, E, and omega is a weighted graph. So X is a finite set of nodes, let's say these blue dots here. Whereas E is a set of edges, so this green line that connects the nodes. Omega is some sort of weight function on the space, on the set of edges, which means that it's just simply weight also with some number, the corresponding edge between X and Y. So this is the setting. So and the aim is to define a reasonable notion of transport distance between probability measures supported on this graph. And there is some sort of coherent with the definition we have at the continuous level. And whereas the static formulation was not very sort of reasonable definition at this level for sort of deeper reasons, there is a very natural discretization of this dynamical formulation. They can be used also at the discrete level. This has been introduced by Jan Maas, my supervisor, and at the same time independently by Alexander Milke. And it reads as follows. It's a discretization of the previous formula. So for two measures M0 and M1 on the space of measures over the graph, over the nodes, I define a distance from M0 to M1 in the similar way. I have a variational problem here. So I minimize a sort of kinetic energy. I will come back now because there is a sort of intrusion in this definition. But let me first discuss the constraint. The constraint is simply the discrete version of the continuity equation. Okay, this continuity equation is the continuous one. And here, instead of having the divergence, as often happens, once we move from continuous to discrete, derivatives become sums. So here is the discrete definition of the divergence. Okay, so these are natural discrete counterparts of what was this equation at the continuous level. The action, the energy we want to minimize is a bit more tricky. Okay, because in some sense, I have still the quadratic term here in the same way as here we had the flux to the power 2. But we want to divide by this strange quantity. So this is simply the density. So mt divided by pi is the density. But theta is a given average function. So think about this as, for example, the arithmetic mean or the geometric mean. The main takeaway message here is that in the discrete space is a bit more ambiguity at this level because the density is defined on the nodes, whereas the natural space where you define the flux is on the edge. So if I want to make a multiplication here, I need first to take an average of the density, and in the way I take the average can be arbitrary. And you're going to see later that in fact the choice of the average can be a non-trivial choice. So the behavior of this distance can be really sensitive to the choice of the average, which is not clear a priori. Okay, but in general, just remember that the discrete definition is a natural discrete version of the Benhamou-Benet formula. Okay, so this is the general setting, but what I want to focus is a particular discrete space, which is the one arising from the final volume setup. Final volume framework, I mean the classical sort of numerical analysis framework, which is used to to give approximation results for PDEs. Okay, I'm far from being applied, I have to admit, but the setting is the same, and I want to take it as an inspiration to describe you a useful discrete-to-continuum approximation result. So the setting is the following. We take a convex set omega, and we just take a partition into convex cells. So T denotes a partition in convex cells, and we also have sort of central points associated with a corresponding cell. If I want to fix the discrete setting, I need to give you all the objects I told you before. So set the reference measure, which actually I didn't really stress too much, but we need to have a sort of reference measure to talk about the densities. And the easiest choice you can have in mind, the reference measure associated to an element of the partition is simply the Lebesgue measure of the cell. I need to choose the weights. Weights is a bit more tricky. So first of all, we say that 2 points are connected by an edge if they are adjacent. Adjacent, I mean the fact that they share an interface, like in this picture. Okay, and then the weights on this edge is proportional to the measure of the surface of the intersection here, this intersection of the boundaries. And it's also inversional proportional to the distance of the points. So the reason of this choice, first sight, it is not very clear, but it is the reasonable choice in order to get suitable approximation results. And I will come back on this later. The third thing I need to choose is the famous average I talked to you about before. Okay, and here the choice is very peculiar. The choice of the average for this final volume partition is this logarithmic mean. I don't know about you, the first time I saw this, it was not exactly the first average I had in mind. You can imagine about the arithmetic mean, the geometric mean, but it turned out that the right average to talk about here is this strange logarithmic average of the density. So I will come back also on this later, but the point is that given the reference measure, the weights and the average, then I can simply define the distance in the way I told you before. Okay, this discrete contribution with the logarithmic average here, and the infimum along the solution to the discrete continuity equation. So let me say one thing, spend one slide on why should we consider this strange logarithmic average. Okay, this has been introduced exactly in the work of Jan Maas and Alexander Milke. So the choice is really concerning the gradient flow structures, okay? So if you now consider exactly the discrete counterparts of what I explained before about the Fokker-Planck equation, you want to look at the discrete entropy functional. So the discrete entropy functional is essentially the discrete version of what I said before. It's a function from the space of measure to R, and it's exactly given by, instead of the integral, we just simply take the sum of R log R times the reference measure pi. If now I consider this function here and I take the gradient flow with respect to the distance with this particular choice of the theta, then I get exactly what is known in literature by the graph heat flow. Graph heat flow, I mean the sort of discrete version of the heat flow, so R dot equal Laplacian of R, where the Laplacian here is the discrete Laplacian associated to this structure. The discrete Laplacian is given by this, again, the differential structure becomes sums and differences, and the weight of the Laplacian is exactly given by this omega divided by pi. Here is the only point where I can try to convince you that the choice of the weights is actually the good one, because if you try to make some scaling arguments, you easily see that this object here scales like 1 divided by the distance square. Okay, if our hope is to have an approximation of the Laplacian, this should look like a difference divided by the distance square, because we have a second order operator. And this is the reason why, one of the reasons why we choose this particular weights. Okay, of course, in the same sort of way as in the infinite dimensional continuous setting, we can also rewrite this equation using the ADI formulation. So this equation with this particular choice of the logarithmic average can be equivalently recast as solution of this energy dissipation inequality, where everything is now discrete. So this is a discrete entropy, and these are simply the discrete slope and metric derivative in the same way we defined it in the continuous phase. To be clear, I brought gradient here because I want to stress that we are in fact in a finite dimensional setting, so the slope is in fact a bit of an overkill in the sense one can really talk about the gradient, and this is exactly the modulus of the gradient. But let's say for the sake of coherence, we stick to this definition as in the continuous setting. Okay, so the point of all this discussion is that in some sense we have a very nice structure both at the continuous level and at the discrete level to talk about optimal transport and gradient flows. So I guess, in my opinion, a natural question is, can we use this structure to obtain discrete-to-continuum approximation results? Okay, so what I want to present here in the second part is, what are these discrete-to-continuum approximation problems? Okay, let's come back to the same framework I described before. This is this final volume setup with the same choice of measures and weights. And what I'm interested in is to consider a sequence of partitions, T, which are shrinking and shrinking with a diameter that goes to 0, and try to study the behavior of this structure when the partition is approximating the continuous set. So the first question is about the solution of the heat flow. And here there is a very nice solution, which is the reason why we choose these particular weights. That in this setting, one can prove that discrete heat flow converges in a suitable sense to the continuous heat flow. So in some sense, this gives you, if you want to think about from a numerical analysis point of view, a nice way to approximate the continuous Fokker-Planck equation using finite dimensional approximations. The, in my opinion, very surprising fact is that despite the convergence of the heat flow, the distance is a total other story, is a total different story. The distance, even though the convergence of the flow happens, might fail to converge to the continuous one. So the discrete distance WT does not always converge to W2, despite it's being defined exactly by a discretization of the continuous one. So in the last part of this talk, I want to give you some examples and discussion about why these two things are behaving differently and what can we say about this. Okay, so let me start from the second problem, so the convergence of the distance. There has been like a result in this framework, and I will talk about this actually in a bit more general setting. Here, I chose this choice of theta because it's the one that also in numerical analysis is used. But in fact, these results are just valid for all symmetric averages. So you can also apply this to arithmetic mean, geometric mean, and stuff like this. But a couple of years ago, Yammas Eva Kopfer and Peter Gladbach proved the convergence of the distance to the continuous one is not always happening, but is in fact equivalent to an additional condition, which is called asymptotic isotopic condition. I brought here the condition, and I don't know about you, but the first time I saw this condition, it wasn't really clear to me what was the meaning, the geometric meaning of this. For example, why do we call this isotopic condition? There is a way to discuss about this from a geometric perspective. It's a bit complicated. What I want to do here to sort of more leave the intuition of this is to give you a slightly stronger condition that implies this one, which is very clear from a geometric perspective. This condition is called center mass condition. Okay, so take this picture. So we have here a set omega, which is a bit more sort of polygonal, and we take this final volume partition. Okay, we say that a center mass condition holds in mathematical terms like this if the following thing happens. Take these two cells, A and B, and take the 2 points, XA and XB. If the line between the points, XA and XB, is cut in half, exactly in the middle point of the interface, then we say the center mass condition is satisfied. So here we have the center mass of the interface, and here is the middle point between the center of the cells. So of course you can understand here that this condition is a very strong symmetry condition. So to cut exactly in half, you have a sort of symmetry assumption on the mesh. It's possible to prove that this implies the isotopic condition, for example. I have also other pictures, just to add also other picture from the paper of Jan, Eva, and Peter. So this one was the first one that I described you now. It's another example of a partition that satisfies the center mass condition. Here is a bit different, right? Because if you draw the line between the points, it's not cut, sorry, exactly in half. But if you look closely, it's easy to see that if you translate originally all the points, you can push everything back in a very symmetric structure. And given the fact that this condition is actually invariant by translation, this is also an example that does not satisfy the center mass condition, but in fact satisfies the isotopic condition, and the convergence of the distance happens. This is, I will not talk too much about this because it's not really split in half, but it's still very symmetric. And if you adapt the average in a sort of weighted way, you can still obtain the convergence. So there are some positive results in this setting, but I will not discuss about this. Much more interesting, in my opinion, is this picture. This picture is not satisfying neither the center mass condition nor the isotopic condition. And there is no way you can put the points around to make it satisfied. In some sense, the points should all be into the center of the cross, and this is not allowed. So this is an example where, for example, the discrete distance is not converging to the continuous one. And it is still sort of symmetric in some sense, which is a bit surprising about the fact that this is not behaving nicely here. So the first question that has been addressed in my PhD was, okay, what is happening here? So why this is happening, and moreover, what can we say when the isotopic condition is not satisfied? Can we still say something about the distance? Can we understand why the distance is not converging? And can we characterize the limits of this distance? So this is exactly the question I wanted to explain in this slide. So suppose we want to discuss about this problem, but we don't have the isotopic condition. What we did is to focus on a bit more specific setting, which is the setting of periodic partitions, like in this picture. So I do that. We are interested in the following picture. Okay, we take a partition of a set, like the one on the left, and then we simply rescale this partition, making many copies of it on a scale 1/n. So in this picture, n should be 3, and we get 9 copies in R2. So, and we get another partition of the cube, okay, but with a finer mesh. The partition is a bit more regular because it's periodic, okay? But in general, you can easily come up with an example where this partition is not satisfying the isotopic condition. So in some sense, we don't expect always to have the convergence to the Wasserstein 2. And the question is, what can we say about the limit in this case? Let's make even an easier simplification. So let's move to one-dimensional. Okay, so the one-dimensional picture, instead of this picture here on the left, we just simply take a partition of the line into space cell M cells, sorry, and with some points X, and the cell of size is pi k. Okay, and we then rescale it, and we ask ourselves, so what can we say about the limits of the distance? And what we proved, together with Jan Mas, Eva Kopfer, and Peter Gladbach, the space, the corresponding probability space with the distance, converges in some suitable sense, in the Gromov-Waltz sense, to the continuous space on the circle, but the limit distance this time is not Vasten2, but is in fact a multiple of Vasten2, and this multiple is depending on both the choice of the average we use and on the geometry of the mesh we started from, so the point X and the position pi. Moreover, the cost here, the sort of the limit cost, the constants here, can be in fact computed explicitly in terms of what usually people in homogenization call a cell problem. So this is essentially a problem, a periodic problem on a single cell, and this minimization problem gives you exactly the constants you have to put here to get the limit in behavior of the distance. So one can prove that this is always more than 1, and is in fact equal to 1 if and only if you have the isotopic condition, which is what we expect. So without the isotopic condition, we don't have Vasten the limit, but we're still able to characterize the limit in a totally explicit way. This is the one-dimensional case. We're in fact working also on the multidimensional case, and it is in the final stage of preparation. And in fact, we also moved a bit more into generalization at the level of the energy. Here, we are studying the energy of this kind, the classical optimal transportation cost with quadratic cost. But in fact, our results extends also to more general energies. And what I mean with more general energies, I mean something like this. Okay, so the high dimensional picture is, instead of being on the line, we have a periodic graph on dimension D. And instead of having the quadratic energy here, we allow to have a sort of general convex function with some technical assumption, function of the mass and of the flux, still under the constraint of the continuity equation. So in this picture here, the F is simply quadratic in the last argument, and depending on, in this way, on the density. But this here can be just simply any convex energy. And also in this case, what we're able to prove is that after suitable rescaling, we have a limit transport problem, which is a sort of homogenized version of the discrete one, once again. And it looks a lot like a Benabou-Bernoulli formula, with the difference that this guy here is not the quadratic energy. Okay, if we start from the quadratic energy, we get something which is more, will be likely to quadratic, but in general, you get simply some homogenized local density F1 that depends on the convex energy we chosen at the beginning via suitable cell formula, which is a sort of high dimensional generalization what we obtain in the one-dimensional picture. Here, the situation is much more complicated because the one-dimensional setting is much easier to handle. It's a very nice tools which are typical in the one-dimensional setting. Here, the cell formula is more complicated. It's not a multiple of the distance, for example. It's something can be much more involved, and the proofs themselves relies on very, very different techniques. But the idea is very similar. Again, we get some behavior in the limit explicit, which is depending on the approximation problem. And also in this setting, if you consider quadratic energy, we can prove that you converge to Vasten2 if and only if you have the isotopic condition. Okay, so in the last few slides, so this was about the convergence of the distance, or more in general, the convergence of the transport problems. But I also talked to you about the usefulness of this problem and this interpretation in the setting of gradient flows. So I want to convince you that this is in fact the case. We can use this structure and these ideas to prove approximation results for gradient flows. So this is the general formulation of a Western gradient flows. I show you this before in the setting of the Fokker-Planck equation, but this is in fact more general. And I recall here again, what do I mean with this? So the continuous level, we have the Vasten2 at the corresponding EDI inequality. But at the same time, we have also the discrete level. We have a partition, a discrete Vasten-like distance on the space of probability. measures, and then we also have the discrete version of the gradient flows. So the questions here is, can I use the gradient flow structure to prove that if I now take solution to this equation and I make the mesh shrink, can I obtain a convergence to the continuous PD? Because this will allow me to have an approximation procedure for the PDEs. So to understand what do I mean with using the gradient flow structure, I use one slide, only one slide, I promise, to discuss about what the main idea how to use this gradient flow structure. And this goes back to the very nice work of Sandia and Sefati in 2004, where they proposed this stability result for gradient flows. The idea is somehow very simple, I think, after all the introduction. But we first start from the discrete level, we fix some initial datum, and we consider the solution MT tau or TMTT of this discrete gradient flow. So the second step is, first we prove a sort of compactness result for the solution of these equations as t goes to 0. And to do this, we need to assume something on initial datum, and this is called the well-preparedness of the initial datum. So assume that the initial datum are converging in a suitable sense to a limiting measure, and also that the energy of the initial datum is converging. Okay, but these conditions, these assumptions are only on the initial datum. And if you are a guy in numerical analysis, you choose how to discretize initial datum. And it will be, you would like to get a procedure to approximate the solution of the evolution equation. So the first step is assuming this well-preparedness, show that you have a compactness result. So that MT converge as t goes to 0 to some curve, mu t, in the space of the probability measure over the Euclidean space. At this moment, you have no idea about what mu t is. Our goal, of course, is to prove that mu t is in fact exactly the solution to the continuous gradient flow equation, for example, to the continuous Fourier-Planck equation. And to do so, you can try to pass to the limit directly at the level of this ADI inequality. So if we're able to pass to the limit each of these terms, then maybe we're able to prove that mu t satisfies the same energy dissipation inequality but at the continuous level. In other words, if we're able to prove a result of this kind, so if we can pass to limit the energy, the meteor derivative, and the slope, so these are the two terms appearing in the dissipation part, then of course, because these three guys are satisfying this energy dissipation inequality, then I can deduce directly from this that mu t must satisfy the continuous gradient flow equation. Okay, because in some sense I can prove from this inequality that these guys are satisfying the energy dissipation inequality for the continuous problem. And this property here, if for any of you that knows gamma convergence, really looks like a sort of gamma limit convergence in space and time, especially for these two things. It's a much more variational approach to the approximation results. There are many results in literature where they prove the convergence of linear equation, but they are based mostly on techniques which are not really variational, but more into a framework of semi-group theory or more classical results. This is really a sort of more variational approach to the problem. They use these gradient flow structures. Okay, this is a general picture of Sandia's inequality, and we can simply apply this to our setting. Okay, so in our setting, if you consider the Fourier-Planck equation, which is exactly given by this equation here for the relative entropy, then in dimension 1, this has actually been already obtained in a work by Dissel and Leo in 2015, where they proved in dimension 1 and for symmetric isotopic meshes, these convergence of the flows using the gradient flow structures. Once again, the proof, as they also say, they say in the paper, is really based on the one-dimensional setting. And what we did together with Dominic Fourcade is that we proved this evolutionary gamma convergence of this evolutionary equation in any dimension. And in fact, we did this even without assuming the isotopic condition. I told you before that the heat flow is expected to be converging also when you don't have isotopy. But in some sense, the distance is not converging when we don't have isotopy. And if you look about the gradient structure, it's clear that the gradient flow structure is depending on the distances. So it's not so trivial, like you can carry out this program also when you don't have isotopic condition. But in fact, we're able to do this And the reason why we can do this, which is a key observation as a final takeaway message here, is that the solution to the gradient flows equation tends to be much more regular than a generic curve in the space of measures. The heat flow at the continuous level is well known to be very, very regularizing. And in fact, what we can prove here is also that discrete flows are uniformly very regular in the sense of all their regularity. In some sense, the discrete flow is not oscillating too much between the cells. And in the convergence of the distance, the reason why the geometry of the mesh was very important is because we can have density which oscillate a lot. In the case of the gradient flows, the fact that we only need to look at the solution of the gradient flows, the fact that we have regularity allows us to not care too much about the lack of symmetry and still get the result in a more general setting. Okay, that's essentially everything. So just to sum up, so the two things I hope I gave you about an intuition of what we were trying to do here are essentially two pictures. One is the results at the level of the transport cost, this homogenization results for transport costs, and or more specifically about the optimum transportation distances, and also these evolutionary gamma convergence results for the discretization of Fokker-Planck equations. Just a quick overview of the possible fitted directions based on these ideas. First of all, as I said, this gradient flow structure is much more general than the Fokker-Planck equation. And more importantly, it does not only apply to linear or even first order PDEs. So for example, the Portinale medium equation is a very famous equation that can be written as gradient flows with respect to Wasserstein, and it is a non-linear PDE. As I said, there are many techniques based on linear evolution to get approximation results. I think it's very interesting to understand whether these ideas, which easily generalize to nonlinear setting, can be used, in fact, to give easy proof of convergence results, and why not maybe also some new approximation results. The second thing that I have in mind is also to study more general gradient flow equations. I talked about the gradient flow with respect to Wasserstein 2, but I told you that we obtain results for more general transport cost. One can in fact look at generalized gradient flows with respect to more general transport cost to describe, for example, conservative laws or other general evolution equation. And it would be nice to understand whether we can get some results and approximation results for more general gradient flow evolutions. And finally, the whole discussion I presented here today is purely deterministic. There's absolutely no randomness involved. The graph is simply a sequence of deterministic graphs, and the results are purely deterministic. In fact, Nicolas Trillos proposed a more stochastic approach in 2017, where he studied essentially random point clouds on the torus. So the setting is very similar, but the points are not given, just simply obtained by a random realization of point clouds on the torus. But the setting is very different. He gets some sort of approximation result to the continuous Wasserstein 2, but the number of connecting edges of each point is almost surely going to plus infinity. So in some sense, you need to have many connections between the points, which is not exactly what happens in the deterministic setting. We simply have a fixed number of neighbors. And so there is a huge gap between deterministic and stochastic world, and we were very interested to understand whether there is a sort of connection between the two and whether our ideas in deterministic settings can be applied also to study more complicated stochastic pictures. And that's it. Thank you very much.
Thank you, Lorenzo, for your seminar. Now it's the moment for questions. If somebody has a question, he can unmute himself and ask a question. Or write and read the question. Okay, I have two questions. Mm-hmm. One is, maybe I was confused. When you define the slope of the discrete energy functional,
Sure, go if you want there.
At the beginning.
Mm-hmm. Yes.
Yeah. What it means that there is a metric on the graph. What it means lim sup as f converges to m.
I mean, in this case, I mean, before it was in the space of measures, it's the same meaning as in the continuous setting. F just simply.
F is yes.
Sorry,
yeah.
I use F and M to focus a bit more about the fact that they were discrete spaces, but this is a measure.
So in the space of graph, we don't have anything. We just define a metric space of probability measure on the graph. Okay.
Exactly. Mm-hmm.
Another question: is it this result of the fact that evolutionary PD can be approximated by this discrete way?
Yes.
Are there some is this technique used for numerical simulations, for instance, of partial differential equations?
So I mean, in fact, let's say the picture can be really sort of, there are simulations in numerical analysis that uses these structures. The proof of the convergence of the algorithm is different. I mean, they didn't use this gradient flow structure, but the equations they use, they are sort of included in this picture. So some of the sort of approximation that the people in numerical analysis uses, it's really equivalent to this inequality here. So they use exactly this equation. Their theoretical results are not obtained using this structure. So we sort of reproved also the convergence of their algorithm. But the equation is really this. They use exactly this framework, even if they don't talk about gradient flows.
Okay.
And for non-linear equations, these I don't know. And there may be something around, but not too much. Maybe they use other techniques.
No, just was my curiosity because I don't know, for what, I'm not an expert, but it seems to me that, for instance, finite element methods, since it depends on weak formulation, it needs the PD to be linear, while this technique you can use also to approximate maybe, I don't know, nonlinear PDs.
You're absolutely right. That's exactly what I wanted. Maybe I didn't say to clear out the last point of possible directions. Exactly. So they have the same equations, but they use weak formulations. So what they do is they prove convergence in H-1 or this kind of dual spaces, which are very highly relying on the linear setting. So those results are for linear evolutions. But this structure is perfectly suitable also for a linear equation. And our work was started from a toy model, but then of course the goal would be to try to do the same thing to provide algorithms for nonlinear evolutions as well, like Born's medium, for example.
Mm-hmm. Thank you.
Welcome.
Okay, it seems to me that there are no other questions, so I propose to thank Lorenzo again, and we meet as usual next Friday. Bye-bye.